All right, we'll go ahead and get started. Hi, everyone. Welcome to I Want to Shard My Database. Now what? This session is being presented by Conor Watson and Nadja Müller, and I'll hand it over to Conor and Nadja to kick us off.
Perfect. Thank you very much. Hi, guys. We're going to talk about sharding Neo4j and how we scale and the new Infinigraph product that we've launched. So we essentially have three forms of scalability at Neo4j. We have replicated graph, which is autonomous clustering. So this is for a graph that fits on a single machine already, and you move that to a clustered environment, and then you can add primaries and secondaries for read scalability and high availability. We have composite, which can be used ideally for federated graphs. So you have very distinct graphs that you want to do some aggregation or some querying that may touch both of those graphs. And then we have Infinigraph, which is a single graph which is shared across many machines in a clustered environment. So we're going to discuss Infinigraph here. So a quick look back at composite. So we have this is a product that allows you to query multiple databases at the same time. You kind of choose how you split your data, but it requires you to know this split and change your queries accordingly. So in this case, we have sales from 2010 and 2011 linked together in a composite database. These databases can be queried individually, or you can use a query like the example here to kind of do some kind of join on these two graphs and introspect on them this way. And then we have sharded property database. This is Infinigraph. This is like stage one of Infinigraph. And essentially, we have a split graph. So Neo4j splits your data into a singular graph shard, maintaining the topology from the original graph. And then you get n property shards, basically containing all of your properties. So each node and relationship that you create on your topology graph will get a duplicate allocated on one of the property shards, and that will hold all of the properties associated with that particular entity. And this way, because we own the splitting, you don't have to change your Cypher queries at all. You just run regular Cypher, and we handle the rest. So why should you shard your database? Ideally, there's kind of one main reason, which is operationally running your database is not possible at the scale you want to go to. So like on commodity hardware, sort of 1 to 3 terabytes, single graphs can grow larger than that, but this is sort of where we've been targeting so far. Or on the other hand, you know that your database is going to grow quite quickly outside of these constraints, although you can split an existing database to be sharded later, which we'll cover in a moment. There's a couple of workloads that this works really well for. So as mentioned before, if you have a single large graph, particularly graphs with large volumes of properties or very heavy properties, so it's ideal for vectors and full text search, or you have some like analytical queries that you currently can't run because the data you want to run them on is too big, then this can allow you to do so. Some considerations you have to take into account are that the topology of the graph remains intact, which whilst is a big benefit because it means that your traversal queries will remain the same performance, it means that there's a fixed size by which you can scale, i.e. you can only scale as far as the graph shard can scale. So you need to be able to fit your topology into a single Neo4j server still. But extending your RAM ratios to disk and having larger single machines can then add even more scale. So I have a quick run through the architecture. So this is what the structure looks like of a sharded property database. So we have a virtual database at the top, and this will be the database that your users will interact with, that you'll interact with when you're running Cypher queries, just as you would expect. It's just, in this case, we've created a sharded database called Neo4j, and that gives you your virtual database there. And then it will create some components to that database. It will create your graph shard, which will be called Neo4j-G000. And then it will create a number of property shards that you specify when you create it. In this case, we've created 3. So you can still use all of the functionality from the original example, the clustered environment. So you can still have many primaries for your graph shard. You can still have, and you can also have replicas for your property shards, which gives you your high availability and also your read scalability. very quickly, sort of how we handle reading in this environment. So we have, if you have no properties when you do a read, so in this case, we just want to, do a normal traversal, go from some node to some other node where it's joined by a relationship with a label, and then return that count. In this case, everything that we need to do this query exists in the topology. So therefore, we just stay in the graph shard. We don't do any network calls. Everything will remain the same speed that you have now and that you would expect, even though it's running in a multi-terabyte database. Then this is where we have to start getting some properties. Here, we want to do the same query, but instead of a count, we want to return all of some property from node M. In this case, we'll do the traversal as we would before. That would remain the same. And then we batch all of the M's that you want to get from your shards. So if we have, let's say that this query returns 100 M's, we will batch those into 100 or into 100 divided by how many property shards you have, and send those off in parallel. And then each of the property shards will basically do a query themselves into their own Neo4j databases, return M and their properties, and then stream that back to the graph shard, and then they'll get sent back to you. So that you can see the query underneath is the query that would get run on the property shards. So the graph shard would essentially grab the node IDs from the traversal, send those down to all the property shards. That query would happen on those, return back, and then we would be able to return those properties to you. We have some very efficient coding, and because we know exactly what we're expecting and what we send in, we can bypass some of the extra stuff from the driver, because we use the Java driver internally to do this, and Neo4j databases on the property shards to serve the properties. And then some stuff that we can do, because we own both sides of this. We own the graph shard and we own the property shard, and they're both Neo4j databases. We can then start to use things like indexes on those property shards. So in this case, we have the same query again, except this time we only want to return properties that are greater than 10. So we would do the exact same thing as before. The traversal would happen on the main graph. We would batch up those property reads, except we'd also send a filter down. The property shards would then run the query below and essentially only return the properties that match that filter. So we get to do that filtering in parallel on all of the shards and return them back, which saves time and CPU usage on the graph shard. And this is quite a simple example, but you can see as you get more complex filters or potentially larger data sets in the terabytes that we're talking about, this is quite a big saving on what you might expect. And then writes, we also have transactional writes in this system. We have the same level of ACID compliance that you'd expect from a normal Neo4j. The writes are committed on the graph shard, and the property shards are not involved in this consensus in any way. They do have a part to play, but not in the consensus of a particular transaction. The property shards, once a commit has happened, which I'll go through in a minute, the property shards basically asynchronously pull these transactions from the graph shard and apply a filtered view of the full transaction log. So as you make a new commit, that would be committed to the transaction log. The property shards would pull this transaction log and apply only the things that it needs to know about. So if it owns property shard 1, then it would apply transactions which relate to node 1. And then the same as normal Neo4j, we can use bookmarks to guarantee read or write consistency, which is what you would expect from normal Neo4j. Nothing's changed there. The point being that everything that you would expect from normal Neo, we expect to give you from this as well. And your operational model looks very similar. So here's a small example. So here we're going to create a node with a property on it, 12. We'd send that create through to the virtual database. The virtual database would then send that through to the graph shard, which if you were using like, if this example said like property 12, instead of property 12, property would equal some other property from some other node, then we might need to do some queries to the property shard like we would not do normally. And that would use the same read path that we saw before. But in this case, we just create this. So the graph shard does the normal writing. It does for the topology bits that you would expect. Then basically during the commit process, the graph shard would talk to the property shard and say, okay, if I was going to write this property into your database, what command would you use to do that? That would then get sent back to the graph shard, and any locking that might need to happen because of that will happen. Then the normal commit process is followed. So the graph shards, if you have multiple primaries, would reach consensus on that write. That would get written to the transaction log, and that point would be committed. And then once it's committed to the transaction log, as I said before, the property shard would pull that transaction log back off the graph shard. Then once that has been applied, the bookmark will be adhered to that you would have passed, that you can pass then to read it. So if you wanted to read this, your query would return a bookmark, the create would return a bookmark. You'd supply that to your driver, or the driver would supply it itself if you've got it configured. And then it would essentially wait for this to be pulled across to the property shard and return the things, return the property that you've written. It can take some time to do this because it needs to pull it and stuff like that. So you have to make sure that you're using bookmarks to make sure that you're reading your writes, the same as normal Neo4j. Okay, so I'll pass over to Nadja, who's going to go through how to create one of these things.
Indeed. So if you want to create a sharded property database, we're going to go through a couple of scenarios on different ways to do that. The first one is creating an empty database. So if you want to create an empty database, depending on if you want to run it on a cluster or just test it on a single machine, you want to do that first. And then you can run this Cypher query that you can see here. So it's in Cypher 25 only, and it has two clauses that are added to the normal create database syntax. So there's the graph shard, which lets you set the topology of the graph shard, which is primaries and secondaries. And then you also have a property shard clause, which lets you set the number of properties and the topology of the property shards. If you're setting up a cluster, there's one thing to keep in mind. So the graph shard requires more resources than a property shard typically, as they also process the data retrieved from the property shards. And the way you can do that is by configuring your server. So in the example below, we define that the only database that can be hosted on that server is the graph shard. If you want to, so the second scenario is you already have a standard Neo4j database and you want to turn it into a sharded property database. That you can do with the Neo4j administration tools that lets you split the database store into multiple shards or multiple stores. And the command that you can use for that is the database copy command. And the way you can define the number of shards is with this property shard count flag. And this is the main difference of making it into a sharded database. After you have done that, you can set up your cluster with the correct numbers of servers and execute the create database command as seen before. Here in the example below, we loaded, we used the target format backup and we loaded up the stores on an S3 bucket. So you can use the option cduri to import those stores into your database. Next scenario is you already have a sharded database, but you want to reshard it. So works exactly the same. You can use the same command. You just need to specify, or in this example, we take a sharded database, make it resharded, change the number of property shards in the property shard can flag, done. And the last scenario is, so if you create an empty database and use Cypher to load data into the database, this is potentially slower than doing an offline import. So the way you can do an offline import into your sharded database is also with a Neo4j admin command. In this case, example, we have database import, full database import, and we specify a bunch of CSV that we're going to load into. And same as before, we have a flag for property shard count, and this kind of defines that it's going to be a sharded property database. And same as before, you set up a cluster, you execute the Cypher command to kind of take the stores and create the database in your DBMS. Once you have your database, let's have a closer look at changes that we had in Cypher for sharded property database. And as we said before, if you query the database, you can use the same Cypher commands as before, and essentially all Cypher is supported. However, the performance model behind it has changed a little bit. So this is partially because we have some inherent network latency when you reach out to the graph shard, to the property shards. But also, as we've seen in Conor's example, sometimes you can also do some of the computation that you would have done in a single graph on the property shards in parallel, so that can also benefit you. However, even with the optimization and everything, occasionally you might hit an unoptimized case right now, and that might hurt. Yeah, what else is there? So it can happen that in some Cypher queries where you would get a graph name, instead of getting the virtual database name, it will now get the graph shard name. So an example of this is the procedure db.info. So because this procedure is executed on the graph shard itself, we decided to return a more specific value, and we are returning the graph shard name there because that's where the procedure is going to be executed. And yeah, last but not least, you cannot directly access the shards and query the shards. So if you want to query your sharded property database, you have to query it over the virtual database name. There are some features that are currently not supported, and among these is change data capture. And this is actually going to be released soon for property sharding. And another one that is not currently not supported is property-based access control, which meaning RBAC if that is based on a specific property value. If you're interested in the performance of property sharding, there are a couple of exceptions that we listed in the documentation, and they also list how you can work around those problems right now. One of these examples is the merge clause, and which is slow for large batches. So an example below, if you have a big CSV file and you want to merge this into your database, it might be slow. So when you look more at the administration commands in Cypher, those look slightly different for sharded property database. And one of these places where you can see that there are changes is in show database. If you run show databases as an administrator, then you will see all the property shards and graph shards associated to your sharded property database. So the first one was the virtual database. The second one is the graph shard, and the graph shard kind of mimics, or the virtual database mimics the location of the graph shards and the secondary primary status. And below you see the property shards, which are, you have 2 lines per property shards because they have a replica. And then you see 4 different types of property shards as well. If you execute show databases as a user, however, so if you don't have any administration rights for databases, database management commands, you will not see the property shards because you can't really do anything with it. So the only thing that you really see is the virtual database. Also interesting to know about show database is that, so the virtual database has a bit different values for some fields. And one of the fields is the current status column. Here we define the current status based on the shards that are underneath the virtual database. So if all status of the shards are the same, the virtual database will have the same status. And if you have different kind of states, the current status will actually have a new state called mixed. And in the status message, you can see which shards or what number of shards have a certain state. So an example, it's one shard that is starting and 2 that is online. Let's also have a look at the show servers. So in show servers, we only show the physical databases that are hosted on the servers. So here you will not see the virtual database Neo4j, but you only see the shards on the different servers as they are allocated. And yeah, so here is a quick overview of some other commands that are like slightly different or something to keep in mind. Yeah, so similar to the create database command we've seen, there's also some alter database syntax that looks very similar actually. and lets you set the topology of the graph shard and all property shards if you wish. Yeah. Then there's also start, stop, and drop database, work the same way as it would for a standard database. However, if you start a database Neo4j and Neo4j is sharded, it will also start all of the shards underneath. And yeah, if you want to define role-based access control, you also need to define that on the virtual database, and it will apply on all the shards as well. There are a couple of places where it makes sense to use the shard name instead. And one of those is, for example, the example we've seen before, really, when you define which databases are allowed to be hosted on a specific server in clusters, cluster management. And another one is we also allow you to define the topology of a specific shard. So yeah, so in this example, we changed the topology of the first property shard to one replica. So this is our last slide. If you're interested in property sharding, please go and try it out. The preview release is out, and it's on 2025.10.1. The documentation is also published, and you can find it in the operations documentations from Neo4j. And the only thing to keep in mind if you want to test it, there's a mandatory setting that you need to enable, sharded property database functionality, where like all the Cypher commands are also behind and stuff. And we also recommend you to set the default language to Cypher 25.
Perfect. I think that's it. I can't see any questions in the chat. If there are any, feel free to fire them in. But we'll be around in the chat if you think of them shortly. But I think that's it from us. Thank you very much.